Okay, so we're moving away from the nucleus now and we're going to the orbital parts. Electrons. So the nucleus defines what an atom is. The nucleus tells us what the atom is. But the electron configuration, so the way the electrons are structured or put together, or arranged is the best word. The way the electrons are arranged defines the chemical properties of the atom. So the atom has particular chemical properties, like it's reactive or it's not reactive, those kind of things. And it's the way the electrons are arranged, or the electron configuration, that tells us all about those properties of that atom. Now the electrons orbit around the nucleus in specified distances or orbits, known as shells. Okay? So what I mean by that is, if this is the nucleus here, okay, in red, you can have an electron here maybe, and an electron here, right? But you can't have an electron sitting in between. That doesn't exist, that doesn't happen. So they sit in very particular places around the nucleus. And if you think about it, that happens sort of similarly in the solar system. You've got sort of Mars, Earth, and all the other planets orbiting a particular place around the sun. They don't kind of interject and sort of move left and right or towards the sun or away from the sun. They always stay in the same orbit. And that's similar to what happens with electrons. They always stay in the same orbit, and that orbit is well defined. And we call that a shell. So the orbit, we call a shell. Now the further away the electron is from the nucleus, the greater the energy that the electron is said to possess. Okay? So the further I am away from the nucleus as an electron, the more likely I am to have more energy. And that kind of makes sense from a planetary point of view as well. So if I hold this pen up here and I drop it, it hits the ground at a certain speed. Now if I take this up higher, further away from the Earth, and I drop it, it will hit at a faster speed. That kind of intuitively tells you that as I take it higher and higher, it has more and more energy because it can hit the ground much faster than when I was lower down. So the same thing applies here. The further I am away from the nucleus, the more energy I'm said to have as an electron. So the shells, because of that, the shells are also said to be called energy levels of electrons. One shell is one energy level, next shell out is another energy level, etc., until infinity. Now, the electron configuration. The goal of an electron is simply to achieve stability. The goal of an atom is simply to achieve stability. So here, this atom, sodium, wants to achieve stability. And there's a reason, and how it does that is what we're going to go through. Now, this stability occurs when the octet rule, so here's an important one, the octet rule, is satisfied. So this is probably the key thing in chemistry that we need to learn first. That when an atom satisfies this octet rule, a stability is achieved. So what is the octet rule? So this rule essentially means that a full outermost shell of electrons is required for stability. So we have to fill the outermost shell of electrons in order to achieve stability. But how many do we have to fill it with? That's our next question. And also, shells must be full before electrons can start filling higher shells. So for instance, I can't just start putting electrons here by taking electrons out of this inner shell, because they have to be full before I can fill the next shell out. I can't have these electrons moving in here to simply satisfy my octet rule. Okay, so there's two parts to the rule, essentially. Okay, so how many shells do we actually need? Or how many electrons do we need in each shell? So in the first shell, 2 electrons are needed to fill it. Okay, so this is a bit of a weird one, but just remember that the first shell, the closest shell, needs 2 electrons, that's all. So helium has 2 electrons, because if you look at the atomic number of helium, it's 2, which means it has 2 protons. And if it has 2 protons, it has 2 electrons. And there's only one shell to start with, so the electrons must fill that shell. Helium is very, very stable, and that explains why, because it's got a full outer shell of electrons with only 2, and so it's extremely stable. It doesn't want to react with anything, because it doesn't need to. Now it gets a little bit more complicated. So therefore, an atom that only has one shell needs 2 electrons to achieve stability. So helium has 2 electrons, and so it's very stable. Okay, so this is what I just mentioned earlier. However, hydrogen has only one electron, so it's not as stable as helium. So it's missing an electron here, which means that it's not stable. And you can see that if you light hydrogen on fire, it will burn. But if you try to light helium on fire, it'll just do nothing. It will just get hot. So you can see there's a difference. All shells after the first require 8 electrons. Okay, so after this shell, okay, so the next shell out, if I was to draw it, now that one would need 8 electrons. And if you look back at sodium, if you just rewind the video a little bit, you'll see sodium. It has 1 electron in its outermost shell, but then each one on the inside has 8, and the innermost one has 2. Okay, so this shell needs 8 electrons. And you can see 8 is usually given the prefix oct. So you can see why it's called the octet rule, because you need 8 electrons in each shell going outwards until you achieve stability. That's why we call it the octet rule, because it always has to do with 8. Okay? Okay, so using electron configurations, is the sodium atom stable? So let's see if we can work this out. So here we have sodium. It's got 11 as its atomic number, as you can see, which means it has 11 electrons. So now each shell has to be filled before the next shell can start filling. So the first shell can only take 2 electrons, so a new shell is needed. So we've got a total of 11 electrons. Okay, first shell takes 2. So how many do we have left? 9. So after we use another shell, we take out, the second shell takes 8. Okay, I might write that a bit neater. So then how many do we have left over? 2 plus 8 is 10, so we have 1 left over. So 1 remains, and therefore it starts a new shell. So in the third shell, we have only 1 electron. And if you look back on the diagram that we had of sodium before, you'll see there's only 1 electron orbiting in the third shell. This shell has only 1 electron, and therefore is short by 7. And so the sodium atom is unstable because it doesn't have 8 in its outermost shell. And that's why. Using electron configurations again, is argon stable? Okay. So you have argon, it's got 18. So the number of electrons equals 8 because proton number equals 18. And number of protons equals the number of electrons. So we have 18 electrons. The first shell stores 2, so the remaining electrons is 16. So we've taken 2 and put them in the first shell, so we have 16 left over. The second shell takes 8 electrons, so we take 8 from our 16 and we put them in the second shell, so we have 8 left over. And then the third shell takes another 8 electrons, so we take another 8 from our 8, and we have 0 electrons left over. And then the third shell has 8 electrons. So it's got the full 8, which means it must be stable. So the outermost shell, the third shell, has 8 electrons, so the argon atom must be stable. Okay?